Tonight, we begin with a story about the night the universe broke. Not a single dramatic explosion. Not a sudden cosmic event. Just a quiet realization in a university office late in the year 1998 that the numbers on a screen did not make sense. And that if those numbers were correct, then everything we thought we understood about the future of the cosmos, about the fate of every star, every galaxy, every atom in existence, was wrong. This is the story of dark energy, the most mysterious force in the universe, the force that makes up roughly 68% of everything that exists, and yet, to this day, no one knows what it is. No one has ever seen it. No one has ever touched it. No one has ever measured it directly. We only know it is there because without it, the universe does not make sense. And now, in the 2020s, even that understanding is crumbling. Welcome to the Science Pillow. Tonight, we are going to journey through one of the most extraordinary stories in the history of science. A story that begins with a simple question about exploding stars and ends with the terrifying possibility that the fundamental nature of reality is not what we were told. Close your eyes. Settle in. Let the darkness behind your eyelids become the darkness of the cosmos itself, and let us begin. To understand the crisis we face today, we need to go back to a time when the universe seemed almost understood. The late 1990s were a remarkable period in cosmology. After decades of uncertainty, scientists had finally assembled a coherent picture of the cosmos. They knew the universe began in a hot, dense state about 13.8 billion years ago. They knew it had been expanding ever since. They had mapped the cosmic microwave background, the faint afterglow of the Big Bang, and found that its patterns matched their predictions with extraordinary precision. But there was one great question that remained unanswered, one question that would determine the ultimate fate of everything. Was the universe going to expand forever, growing colder and darker until every star burned out? Or was gravity going to slow the expansion down, eventually pulling everything back together in a great cosmic collapse? The answer, scientists believed, was somewhere in between. They expected the expansion to be slowing down because gravity pulls things together. Every galaxy pulls on every other galaxy. Every atom pulls on every other atom. And all of that pulling should be acting like a brake on the expansion, gradually slowing it down over time. To measure how fast the expansion was slowing, two competing teams of astronomers set out to observe the most distant exploding stars they could find. These were not ordinary stars. They were a specific type of stellar explosion called a Type 1A supernova. A Type 1A supernova, pronounced Type 1AI, is a very special kind of explosion. It occurs in a binary star system, where two stars orbit each other. One of these stars is a white dwarf, the dense, Earth-sized remnant of a star that has exhausted its nuclear fuel. The white dwarf slowly steals material from its companion star, accumulating mass on its surface. When the white dwarf reaches a critical mass threshold, roughly 1.4 times the mass of our Sun, a value known as the Chandrasekhar limit, pronounced Chandrasekhar, it can no longer support itself against gravitational collapse. The result is a thermonuclear explosion of extraordinary power and, crucially, extraordinary consistency. Because every Type 1A supernova explodes at roughly the same mass, they all produce roughly the same amount of light. This makes them what astronomers call standard candles. If you know how bright something truly is, and you measure how bright it appears from Earth, you can calculate exactly how far away it is. It is the same principle you use when you see a streetlight in the distance. You know how bright a streetlight is supposed to be. If it looks dim, it must be far away. If it looks bright, it must be close. By finding type 1. A supernovae in distant galaxies, astronomers could measure two things at once. The brightness of the supernova told them how far away the galaxy was, and the redshift of the galaxy's light told them how fast it was moving away from us. Redshift is the stretching of light waves caused by the expansion of space itself. The more the light is stretched, the faster the galaxy is receding, and the more the universe has expanded since that light was emitted. Put these two measurements together, distance and recession speed, for enough supernovae across enough of cosmic history, and you can map out exactly how the expansion rate of the universe has changed over time. You can see whether gravity is winning, pulling everything back together, or whether the expansion will continue forever. Two teams took up this challenge. The Supernova Cosmology Project, led by Sol Perlmutter, pronounced Sol Perlmutter, at the Lawrence Berkeley National Laboratory in California, and the High Z Supernova Search Team, led by Brian Schmidt, pronounced Brian Schmidt, at the Australian National University, with Adam Rees, pronounced Adam Rees, playing a crucial role in the data analysis. These two teams were rivals. They competed for telescope time. They competed for the best supernovae. They used different methods, different software, different calibration techniques. If they arrived at the same answer independently, it would be very difficult to argue that both teams had made the same mistake. Through the mid-1990s, both teams accumulated data. They found supernovae in galaxies billions of light-years away. They measured their brightness. They measured their redshift. And then they plotted the results. What they found made no sense. The distant supernovae were dimmer than they should have been. Not brighter. Not exactly the right brightness. Dimmer. Think about what that means. If a supernova is dimmer than expected, it means it is farther away than expected. And if it is farther away than expected, it means the universe has expanded more than expected since that light was emitted. And if the universe has expanded more than expected, it means the expansion is not slowing down. It is speeding up. The expansion of the universe is accelerating. Both teams arrived at this conclusion independently, and both teams initially assumed they had made a mistake. They checked their data. They checked their calibrations. They looked for systematic errors. They considered the possibility that the distant supernovae were being dimmed by cosmic dust, making them appear farther away than they really were. They considered the possibility that Type 1a supernovae in the early universe were intrinsically different from those nearby. They considered every alternative explanation they could think of. None of them worked. The data was clear. The universe was not just expanding. It was expanding faster and faster and faster. Something was pushing it apart. Let that sink in for a moment. For billions of years, the universe had been expanding, and for most of that time, gravity had indeed been slowing the expansion down. But at some point, roughly 5 billion years ago, something changed. Some unknown force began to overpower gravity, not locally, not in individual galaxies or clusters, but everywhere, across the entire fabric of space and time. And this force was winning. It was pushing the universe apart faster than gravity could pull it back together. This was not a small effect. It was not a subtle correction to existing theories. It was a complete overturning of expectations. Every cosmologist alive had assumed the expansion was decelerating. Every model predicted deceleration. Every intuition about gravity said that what goes up must come down, that expansion must slow, that the pull of matter must eventually dominate. Instead, the universe was accelerating, and no one had any idea why. Saul Perlmutter later described the experience of seeing the data for the first time. He said it felt like throwing a ball into the air and watching it fly upward faster and faster, defying gravity, accelerating into the sky with no explanation. Brian Schmidt reportedly told his team that they had probably made a mistake, and they should go back and find it. But they could not find it, because there was no mistake. Adam Rice, who performed the key statistical analysis for the high Z team, later recalled that the result was so unexpected that they spent months looking for errors before they were willing to publish. The idea that the universe was accelerating felt wrong. It felt physically impossible. And yet the data said otherwise. In 1998, both teams published their results within weeks of each other. The Supernova Cosmology Project and the High Z Supernova Search Team independently confirmed that the expansion of the universe was accelerating. The scientific community was stunned. Papers poured in. Conferences were hastily organized. Theorists scrambled to explain what could possibly be causing this acceleration. And very quickly, a name emerged for this unknown force: dark energy. The name itself tells you how little we understand. In physics, when you call something dark, it means you cannot see it. You cannot detect it directly. You know it is there only because of its effects on things you can see. Dark energy is not a substance you can hold. It is not a particle you can detect in a laboratory. It is a label for our ignorance, a placeholder name for whatever it is that is pushing the universe apart. And here is the truly unsettling part. When scientists calculated how much dark energy there must be to account for the observed acceleration, the answer was staggering. Dark energy makes up roughly 68% of the total energy content of the universe. 68%. More than 2/3 of everything that exists is this mysterious, invisible, undetectable force. Add to that the roughly 27% of the universe that is dark matter, another mysterious substance we cannot see or detect directly, and you arrive at a humbling conclusion. Only about 5% of the universe is made of the kind of matter we are familiar with: atoms, protons, neutrons, electrons, the stuff that makes up stars and planets and people and everything you have ever seen or touched. All of that is just 5%. 95% of the universe is something else entirely, something we do not understand, something we have never directly observed, something that, despite decades of effort, remains almost completely mysterious. For the discovery of the accelerating expansion of the universe, Saul Perlmutter, Brian Schmidt, and Adam Rice were awarded the Nobel Prize in Physics in 2011. The Nobel Committee called it a discovery that shook the world of physics. And that is not an exaggeration. It genuinely did. The news rippled through the scientific community with a force that is hard to overstate. Textbooks had to be rewritten. Lecture courses had to be restructured. Entire research programs had to be redirected. Cosmologists who had spent their careers studying the deceleration of the universe suddenly found themselves studying the acceleration. Theoretical physicists who had confidently assumed that the cosmological constant was zero, that empty space had no intrinsic energy, suddenly had to explain why it was not zero, but was instead a tiny, positive number that happened to dominate the energy budget of the universe. The discovery also had a profound philosophical dimension. For centuries, humans had assumed that the universe was fundamentally comprehensible, that with enough effort, enough data, enough mathematical ingenuity, we could understand the basic workings of the cosmos. The discovery of the accelerating expansion did not refute that assumption, but it added a sobering caveat. The universe is comprehensible, but it is also far stranger than we imagined. And the strangeness is not confined to exotic, distant phenomena. It pervades the entire cosmos, every cubic meter of space, including the space you are occupying right now, is filled with dark energy. It is everywhere, always, pushing space apart, and we have no idea what it is. But the Nobel Prize did not come with an explanation. We knew the universe was accelerating. We did not know why. And in the years that followed, as scientists tried to understand dark energy, they discovered something even more troubling. The simplest explanation for dark energy led to one of the worst predictions in the history of science. To understand why, we need to talk about the vacuum. Not a vacuum cleaner. The vacuum of space. The emptiness between stars and galaxies. The void that, at first glance, appears to contain nothing at all. But quantum mechanics tells us that the vacuum is not truly empty. It is alive with activity. Even in the most perfect vacuum, with no particles, no radiation, no matter of any kind, there is still energy. This energy arises from something called quantum fluctuations, the ceaseless random appearance and disappearance of virtual particles that pop into existence and vanish again in unimaginably tiny fractions of a second. These quantum fluctuations give the vacuum a kind of baseline energy. Physicists call it vacuum energy, or zero-point energy. And here is the key connection. When Einstein wrote his equations of general relativity, the theory that describes how gravity works, he included a term called the cosmological constant, represented by the Greek letter lambda. This cosmological constant is mathematically equivalent to vacuum energy. It represents the intrinsic energy of empty space itself. Einstein originally introduced the cosmological constant in 1917, not because of any observation, but because he wanted his equations to describe a static, unchanging universe. At the time, no one knew the universe was expanding. Einstein added the cosmological constant to balance gravity, preventing the universe from collapsing under its own weight. It was a mathematical fix to keep the cosmos still. Then, in 1929, Edwin Hubble discovered that the universe was indeed expanding. Distant galaxies were moving away from us in every direction, and the farther away they were, the faster they were receding. Einstein realized that his cosmological constant had been unnecessary. The universe was not static. It was dynamic, expanding, evolving. He reportedly called the cosmological constant his biggest blunder and abandoned it. For decades, the cosmological constant was treated as a curiosity, a historical footnote, a mistake that Einstein had wisely corrected. But in 1998, when the two supernova teams discovered that the expansion was accelerating, the cosmological constant came roaring back. Because the simplest way to explain an accelerating universe is to say that empty space has a small positive energy, and this energy pushes space apart. The cosmological constant was no longer a blunder. It was a prediction. And this is where the crisis begins. When physicists tried to calculate the value of the cosmological constant from first principles, using quantum field theory to add up all the vacuum energy from all the quantum fluctuations of all the known fields in physics. The answer they got was absurd. The predicted value of vacuum energy was roughly 10 to the power of 120 times larger than the observed value. That is a 1 followed by 120 zeros. It is not an exaggeration to call this the worst prediction in the history of physics. No other scientific prediction has ever been off by such an enormous factor. Let me put this in perspective. If I asked you to estimate the weight of a cat, and you answered that the cat weighs as much as the entire observable universe, you would be off by roughly a factor of 10 to the power of 53. That would be a terrible estimate. But it would be 67 orders of magnitude closer to reality than the quantum field theory prediction for vacuum energy. This discrepancy is known as the cosmological constant problem, and it has haunted physics for over 2 decades. It is, by many accounts, the single biggest unsolved problem in fundamental physics. Not just in cosmology. In all of physics, there are only a few possible resolutions. One is that there is some unknown mechanism, some deep principle of physics we have not yet discovered, that cancels out almost all of the vacuum energy, leaving only the tiny residual amount we observe. But no one has been able to identify what this mechanism might be. Every attempt to construct one has failed. Another possibility is that the cosmological constant is not actually related to vacuum energy at all. Perhaps dark energy is something entirely different, something that just happens to look like a cosmological constant in our current observations, but is actually a dynamic, evolving field that changes over time. And this possibility, the possibility that dark energy is not constant, is at the very heart of the crisis that is unfolding right now. Let us pause here for a moment. You are doing wonderfully. Let the quiet settle around you. Let the mystery of the cosmos hold you gently. There is no hurry. The universe has been expanding for 13.8 billion years. It will still be expanding when you wake. Take a breath, and let us continue. For over 20 years after the 1998 discovery, the cosmological constant model worked. It worked remarkably well. Scientists built an entire framework of the universe. Around it, a framework called the Lambda-CDM model, where lambda stands for the cosmological constant and CDM stands for cold, dark matter. In this model, the universe is made of 3 main ingredients. About 5% ordinary matter, the atoms and molecules we are familiar with. About 27% cold, dark matter, a mysterious substance that clumps together under gravity and provides the scaffolding for galaxies and large-scale structure. And about 68% dark energy, represented by the cosmological constant, a uniform, unchanging energy that fills all of space and drives the accelerating expansion. Lambda-CDM is elegant. It is simple. And for 2 decades it matched virtually every observation with remarkable precision. The cosmic microwave background. The distribution of galaxies across the sky. The abundances of light elements forged in the first few minutes after the Big Bang. The pattern of tiny temperature fluctuations in the oldest light in the universe. All of it fit the Lambda-CDM model beautifully. It was, for a time, the standard model of cosmology, the closest thing we had to a complete description of the universe on the largest scales. Some called it the concordance model, because so many independent lines of evidence all pointed to the same answer. Same proportions, same parameters, same cosmic recipe. But science is not about building monuments to our theories. Science is about testing them, pushing them, looking for the cracks. And in the 2020s, the cracks began to appear. Section 2. The Universe We Built. To truly appreciate the crisis that cosmology faces today, you need to understand what we built. The edifice of modern cosmology is one of the greatest intellectual achievements in human history. It is a story of how we went from looking up at the sky in wonder to constructing a precise quantitative model of the entire observable universe. And it all begins with a single radical idea. The universe had a beginning. For most of human history, the prevailing assumption was that the universe was eternal. It had always existed, and it always would. The stars were fixed. The cosmos was unchanging. This was not just a philosophical belief. It was the dominant scientific view well into the 20th century. Even Einstein, when he formulated general relativity in 1915 and 1916, assumed the universe was static. That is why he introduced the cosmological constant, to prevent his equations from predicting a universe that was either expanding or contracting. But the universe did not cooperate with Einstein's assumption. In 1927, a Belgian priest and physicist named Georges Lemaitre, pronounced Georges Le Maître, published a remarkable paper. Working independently from Einstein's general relativity equations, Lemaitre derived a solution that described an expanding universe. He proposed that the universe was growing, that galaxies were moving apart from each other, and that if you ran the clock backward, everything would converge to a single point, a primeval atom, as he called it, from which the entire universe erupted. 2 years later, Edwin Hubble provided the observational evidence. Using the 100-inch telescope at Mount Wilson Observatory in California, Hubble measured the distances and velocities of nearby galaxies. He found that virtually all of them were moving away from us, and that the farther away a galaxy was, the faster it was receding. This relationship, now known as Hubble's law, or more recently the Hubble-Lemaitre law, was the first direct evidence that the universe was expanding. The implications were profound. If the universe is expanding today, then it was smaller yesterday. And if you trace the expansion backward through time, the universe becomes smaller and denser and hotter the further back you go. Eventually, you reach a point where all the matter and energy in the observable universe was compressed into an unimaginably hot, dense state. And from that state, the expansion began. This is the Big Bang. The Big Bang is one of the most misunderstood concepts in all of science. When most people hear the words Big Bang, they imagine an explosion, a bomb going off in empty space, sending matter flying outward in all directions. But that is not what the Big Bang was. The Big Bang was not an explosion in space. It was an expansion of space. There was no empty space for matter to explode into. Space itself was expanding, carrying matter along with it. Every point in the universe was moving away from every other point. There was no center of the explosion, because the expansion was happening everywhere simultaneously. Imagine the surface of a balloon being inflated. If you draw dots on the balloon with a marker as the balloon inflates, every dot moves away from every other dot. No single dot is the center of the expansion. The expansion is happening everywhere on the surface at once. The universe works the same way, except in 3 dimensions instead of 2. The Big Bang also did not happen at a single point in space. It happened everywhere. At the moment of the Big Bang, the entire observable universe, every galaxy, every star, every atom that would eventually become you and me and the Earth and everything you have ever known, was compressed into an incredibly hot, dense state, and it was all expanding. The Big Bang is not a place, it is a time. It is the moment when the expansion began, roughly 13.8 billion years ago. In the decades following Hubble's discovery, scientists worked to fill in the details of this expanding universe. One of the most important pieces of evidence came from an accidental discovery in 1964. Arno Penzias, pronounced Arno Penzias, and Robert Wilson, two radio astronomers working at Bell Telephone Laboratories in New Jersey, were trying to calibrate a large, horn-shaped radio antenna. No matter what they did, they could not eliminate a persistent, faint hiss of microwave radiation coming from every direction in the sky. They checked their equipment. They cleaned pigeon droppings from the antenna. They pointed it in every possible direction. The hiss remained. What Penzias and Wilson had discovered entirely by accident was the cosmic microwave background, often abbreviated as CMB. This is the oldest light in the universe, emitted roughly 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and light to travel freely for the first time. Before that moment, the universe was a hot, opaque plasma, a blinding fog of protons, electrons, and photons, all interacting so furiously that light could not travel more than a short distance before being absorbed or scattered. But when the temperature dropped below about 3,000 Kelvin, roughly 380,000 years after the Big Bang, something remarkable happened. Electrons and protons combined to form neutral hydrogen atoms, and neutral hydrogen is transparent to light. Suddenly, the photons were free. They have been traveling through the universe ever since, and as the universe expanded, their wavelengths stretched. What was once a blinding white glow has been stretched by the expansion of space into faint microwave radiation, invisible to the human eye but detectable with the right instruments. This is the CMB. It fills the entire universe. It comes from every direction in the sky, and it is extraordinarily uniform, with a temperature of roughly 2.725 Kelvin, or about minus 270.4 degrees Celsius. This temperature is the same everywhere to an accuracy of about 1 part in 100,000. That uniformity is one of the strongest pieces of evidence for the Big Bang. It tells us that the early universe was extraordinarily smooth, extraordinarily hot, and extraordinarily dense. And it confirms that the universe has been expanding and cooling ever since. Penzias and Wilson received the Nobel Prize in Physics in 1978 for their discovery. They had found the echo of creation itself. But the CMB held another secret. While the overall temperature was remarkably uniform, there were tiny, almost imperceptible variations from place to place. These tiny fluctuations, differing by only about 1 part in 100,000 from the average temperature, are called anisotropies, pronounced anisotropies. These fluctuations may seem insignificant, a difference of a few millionths of a degree, but they are, in fact, the most important features in the entire CMB, because these tiny temperature variations correspond to tiny differences in the density of matter in the early universe. Regions that were slightly denser than average had slightly stronger gravity. Over millions and then billions of years, that extra gravity pulled in more matter, which increased the gravity further, which pulled in even more matter. This is the process of gravitational collapse, the slow, patient, relentless accumulation of matter driven by gravity. The tiny fluctuations in the CMB are the seeds from which all structure in the universe grew. Every galaxy, every cluster of galaxies, every cosmic web filament stretching across hundreds of millions of light years, all of it can be traced back to those tiny density variations in the early universe. Scientists have mapped these fluctuations with extraordinary precision, first with the COBE satellite, pronounced Kiobe, launched in 1989, then with the WMAP satellite, pronounced WMAP, launched in 2001, and most recently with the Planck satellite, launched by the European Space Agency in 2009. Each successive mission produced a more detailed map of the CMB, and each confirmed and refined the same basic picture. The universe is 13.8 billion years old. It is geometrically flat, or very close to flat, and its composition is roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. These numbers are not rough estimates. They are precise measurements with uncertainties of less than 1%. The Planck satellite measured the age of the universe to within about 40 million years, the composition to within about 1 percentage point. This is precision cosmology, and for 2 decades, all the numbers agreed. It is worth pausing to appreciate the sheer audacity of this achievement. Human beings living on a tiny planet orbiting an unremarkable star in the suburbs of a spiral galaxy had managed to determine the age, composition, and geometry of the entire observable universe. They had done it by capturing light that had been traveling for 13.8 billion years. Light that was emitted when the universe was a fraction of its current age, when it was 1,000 times hotter and 1 billion times denser than it is today. They had decoded the patterns in that light, translated them into numbers, and from those numbers reconstructed the history of everything. The Planck mission, in particular, was a masterpiece of precision engineering and data analysis. The satellite orbited the second Lagrange point, about 1.5 million kilometers from Earth, where it could observe the sky continuously without interference from the Sun, the Earth, or the Moon. Its detectors were cooled to a fraction of a degree above absolute zero, allowing them to measure the tiny temperature fluctuations in the CMB with exquisite sensitivity. The resulting map, a full sky image of the temperature variations in the oldest light in the universe, is one of the most beautiful and information-rich images in the history of science. From that single image, scientists extracted the fundamental parameters of the cosmos: the density of ordinary matter, the density of dark matter, the density of dark energy, the age of the universe, the geometry of space, the amplitude and spectral index of the primordial fluctuations, all of it encoded in the patterns of hot and cold spots, like a cosmic fingerprint left behind by the Big Bang. The other great pillar of observational cosmology is the large-scale structure of the universe itself, the distribution of galaxies across the sky. If you could zoom out far enough, far beyond individual galaxies, far beyond galaxy clusters, you would see that the universe has a structure. Galaxies are not distributed randomly. They are arranged in a vast three-dimensional web of filaments and sheets, surrounding enormous voids where almost no galaxies exist. This is called the cosmic web. The filaments are made of dark matter and ordinary matter, stretching across hundreds of millions of light years like the threads of an impossibly vast spider web. At the intersections of these filaments, where the density is highest, You find the largest galaxy clusters, massive collections of hundreds or even thousands of galaxies bound together by gravity. The cosmic web is beautiful, intricate, and deeply informative. Its structure carries the imprint of the same physics that shaped the CMB fluctuations. The same density variations that seeded the CMB anisotropies also seeded the growth of the cosmic web. And the way the web has grown over time depends on all the fundamental parameters of the universe: the amount of matter, the amount of dark energy, the expansion rate, the initial conditions. By mapping the cosmic web, by measuring the statistical properties of galaxy clustering, scientists can independently test the Lambda-CDM model. And for years, the results were consistent. The cosmic web looked exactly the way the model predicted. Large galaxy surveys like the Sloan Digital Sky Survey, often called SDSS, pronounced SDSS, mapped the positions and distances of millions of galaxies, building a three-dimensional atlas of the nearby universe. And the patterns they found, the characteristic scale of galaxy clustering, the way that clustering evolves with distance and time, all of it confirmed the Lambda-CDM picture. Everything fit: the CMB, the supernovae, the galaxy surveys, the abundances of light elements, the growth of structure. All the independent lines of evidence converged on the same model with the same parameters, describing the same universe. It was a triumph, a genuine, intellectual triumph. Humanity had constructed a precise quantitative model of the entire observable universe, from the first fraction of a second after the Big Bang to the present day, 13.8 billion years later. But a triumph built on ignorance is a fragile thing. We knew the composition of the universe to exquisite precision: 5% ordinary matter, 27% dark matter, 68% dark energy. But we did not actually know what 95% of it was. We had measured it, we had constrained it, we had given it names, but we had not understood it. And understanding, it turns out, matters. Let the weight of that thought settle over you gently. 95% of the universe is unknown. We built an entire model of the cosmos, and most of it is labeled with our ignorance. But that ignorance was comfortable for a time. The model worked. The numbers fit. The predictions held, until they didn't. Take a slow breath. Feel the quiet around you, and let us move deeper into the story. Section 3. The cracks. Science progresses not just through discoveries, but through disagreements. When two careful measurements of the same thing give different answers, it means one of three things. Either one measurement is wrong, or the other measurement is wrong, or our understanding of what we are measuring is incomplete. In the 2020s, cosmology has been confronted with not one, not two, but multiple disagreements. Multiple cracks in the foundation of the standard model, and the more data we collect, the wider those cracks seem to grow. This is not how it was supposed to go. The 21st century was supposed to be the era of precision cosmology, the era when we refined our measurements, added decimal places to our parameters, and basked in the glow of a model that worked. Instead, the more precisely we measure, the more clearly we see that something does not add up. It is as if you had a map that worked perfectly when you used it at a coarse level, navigating between cities. But when you zoomed in, when you tried to navigate at the street level, you found that the roads were not where the map said they should be. The map was not wrong exactly. It was just not detailed enough to capture the true complexity of the terrain. The standard model of cosmology may be like that map. Good enough for the broad strokes, but missing something essential in the details. And it is in the details that the truth hides. The most famous of these cracks is the Hubble tension. The Hubble constant is the number that describes how fast the universe is expanding right now. It tells you the relationship between the distance of a galaxy and the speed at which it is receding from us. A higher Hubble constant means the universe is expanding faster. A lower Hubble constant means it is expanding more slowly. You might think that measuring the expansion rate of the universe would be straightforward. After all, we have been observing the expansion for nearly a century. But measuring the Hubble constant requires knowing two things very precisely: how far away galaxies are and how fast they are moving. And while measuring speed is relatively easy, because the redshift of a galaxy's light tells you its recession velocity directly, measuring distance is extraordinarily difficult. The problem is that the universe does not come with a ruler. There is no tape measure stretching from Earth to a distant galaxy. Instead, astronomers have to use a series of overlapping techniques, each one calibrated by the one before it, building up a chain of distance measurements that stretches from nearby stars to the most distant galaxies. This chain is called the cosmic distance ladder. The first rung of the ladder uses parallax, the apparent shift in a nearby star's position as Earth orbits the Sun. By measuring this tiny shift, astronomers can calculate the distance to stars within a few thousand light years. The second rung uses a type of pulsating star called a Cepheid variable, pronounced Cepheid. Cepheids have a remarkable property. The period of their pulsation, how long it takes for them to brighten and dim and brighten again, is directly related to their intrinsic luminosity. Brighter Cepheids pulsate more slowly. This means that by measuring a Cepheid's pulsation period, you can determine how bright it truly is, and by comparing that to how bright it appears, you can calculate its distance. Cepheids can be observed in galaxies tens of millions of light years away, and those galaxies can also be observed to contain Type 1a supernovae, the standard candles we discussed earlier. By calibrating the supernovae with the Cepheids and the Cepheids with the parallax measurements, astronomers build the distance ladder rung by rung, extending their reach out to billions of light years. Adam Rice, one of the original discoverers of the accelerating expansion, leads a project called SH0ES, which stands for supernova, H0 for the equation of state. The SH0ES team has spent years refining the cosmic distance ladder, improving the calibration at every step, and their latest measurements of the Hubble constant give a value of about 73 kilometers per second per megaparsec. A megaparsec is a distance of about 3.26 million light years. Now, there is another way to measure the Hubble constant. Instead of using the cosmic distance ladder to measure the expansion rate directly, you can use the cosmic microwave background, the oldest light in the universe, to infer what the expansion rate should be today. The CMB captures a snapshot of the universe as it was roughly 380,000 years after the Big Bang. By measuring the patterns in the CMB, specifically the sizes and intensities of the temperature fluctuations, scientists can determine the fundamental parameters of the universe at that early time: the density of matter, the density of dark energy, the geometry of space, and from those parameters, using the Lambda-CDM model, they can calculate what the expansion rate should be today. The Planck satellite did exactly this, and the value it predicted for the Hubble constant is about 67.4 kilometers per second per megaparsec, 73 versus 67.4. That might not sound like a big difference, but in the context of precision cosmology, it is enormous. Both measurements are incredibly precise. The SH0ES team claims an uncertainty of about 1.4 kilometers per second per megaparsec. The Planck team claims an uncertainty of about 0.5. When you account for these uncertainties, the two values disagree at a level of roughly 5 sigma. In physics, a 5 sigma disagreement means there is only about a 1 in 3.5 million chance that the discrepancy is due to random statistical fluctuations. In other words, it is almost certainly not a coincidence. Something is genuinely different about these two measurements. Either the distance ladder measurements are wrong, or the CMB measurements are wrong. Or, and this is the possibility that keeps cosmologists awake at night, the Lambda-CDM model that connects them is wrong. If the model is wrong, it means that our understanding of how the universe evolved from the early CMB era to today is incomplete. Something happened between the time the CMB was emitted and now that the model does not account for. Some unknown physics that changed the expansion rate in a way we did not anticipate. But the Hubble tension is not the only crack. There is another discrepancy, less famous but equally troubling, called the S8 tension. S8, written as the letter S with a subscript 8, is a parameter that measures how clumpy the universe is today. Specifically, it quantifies the amplitude of matter fluctuations on a scale of 8 megaparsecs, roughly 26 million light-years. The Lambda-CDM model, when calibrated using the Planck CMB data, predicts a specific level of clumpiness. The universe should be a certain amount of lumpy, with a certain amount of structure on a given scale. This prediction can be tested by observing the actual distribution of matter in the universe today, using techniques like gravitational lensing and galaxy clustering surveys. Gravitational lensing is the bending of light by gravity. When light from a distant galaxy passes near a massive object, like a galaxy cluster, the gravity of the cluster bends the light's path, distorting the image of the distant galaxy. By measuring these distortions across large areas of the sky, scientists can map the distribution of matter, including invisible dark matter, in the foreground. Several major surveys have done this, including the Kilo-degree survey, often called KIDS, the Dark Energy Survey, known as DES, and the Hypersuprime Cam survey. And they all find the same thing. The universe is slightly less clumpy than the Lambda-CDM model predicts. The matter is more smoothly distributed than it should be. The fluctuations are smaller. The clumping is weaker. The S8 value measured from these surveys is consistently lower than the value predicted by Planck. The statistical significance of this discrepancy varies depending on the survey and the analysis method, but it generally falls in the range of 2 to 3 sigma. Not as dramatic as the Hubble tension, but persistent and consistent. And, importantly, multiple independent surveys using different instruments and different techniques all point in the same direction. Something about the way matter has clumped together over cosmic time does not match our model. And then there are the galaxies. In 2022, the James Webb Space Telescope, often called JWST, began sending back its first images and data. JWST is the most powerful space telescope ever built, with a primary mirror 6.5 meters across, roughly 2.5 times the diameter of Hubble's mirror. It observes primarily in infrared light, which allows it to see galaxies at extreme distances, galaxies whose light has been red-shifted out of the visible spectrum by the expansion of the universe. Almost immediately, JWST found something unexpected. In the most distant reaches of the universe, at redshifts of 10 and above, corresponding to a time when the universe was only about 300 to 500 million years old, JWST discovered galaxies that were far too massive, far too bright, and far too mature for their age. According to the Lambda-CDM model, galaxies at that early epoch should have been small, faint, and still in the process of forming. The universe simply had not had enough time for large galaxies to assemble. The process of galaxy formation, where dark matter halos grow through gravitational collapse and mergers, accumulating gas that cools and forms stars, is supposed to take hundreds of millions to billions of years. But JWST found galaxies at extremely high redshifts that contained billions of stars. Galaxies that appeared to have formed an enormous amount of stellar mass in a startlingly short time. Some of these galaxies were estimated to be 50 times more massive than the models predicted they should be. One set of galaxies, discovered in the JWST-CEERS survey, pronounced Sears, had stellar masses so high that they would violate the model's predictions even if every available atom of gas in their dark matter halos had been converted into stars with perfect efficiency. In other words, the standard model of galaxy formation could not produce these galaxies even under the most optimistic assumptions. These impossible galaxies, as some astronomers began calling them, sent shockwaves through the community. If confirmed, they represent a serious challenge to the Lambda-CDM model. The model does not just get the numbers slightly wrong, it gets it dramatically wrong. Galaxies that massive, that early, should not exist. Now, it is important to note that some caution is warranted. JWST measures light, not mass directly. The stellar mass estimates depend on models of how stars produce light at different ages and metallicities. Some researchers have argued that the masses might be overestimated due to modeling assumptions. Others have pointed out that extremely active star formation, at rates far exceeding anything seen in the nearby universe, could produce very bright galaxies that are not necessarily as massive as they appear. But as more data has accumulated, and as the analysis techniques have been refined, the basic finding has held up. Even the most conservative estimates still show galaxies at high redshifts that are more massive and more abundant than the Lambda-CDM model predicts. The degree of the tension has decreased somewhat in some analyses, but it has not gone away. And this tension feeds into the broader crisis. It is not just one anomaly. It is not just one measurement that disagrees with the model. It is multiple independent measurements, each probing different aspects of the universe, each finding that the Lambda-CDM model does not quite fit. The Hubble tension, the S8 tension, the impossible galaxies, 3 cracks in the foundation. Each one alone might be explained away as a systematic error, a calibration problem, a statistical fluctuation. But together, they paint a picture of a model that is under siege. There is another anomaly worth mentioning, though it is more subtle and less well-publicized than the others. It involves something called the CMB dipole. As the Earth, the Sun, and the entire Milky Way galaxy move through space, the cosmic microwave background appears slightly hotter in the direction we are moving toward, and slightly cooler in the direction we are moving away from. This is the kinematic dipole, and it is caused by the Doppler effect. the same, phenomenon that makes a siren sound higher-pitched as an ambulance approaches and lower-pitched as it moves away. By measuring the CMB dipole, we can determine our velocity through the universe, our motion relative to the frame of reference defined by the CMB itself. And that velocity, in turn, should be consistent with our motion relative to distant galaxies and radio sources. But recent studies have found a discrepancy. The dipole inferred from the CMB does not match the dipole inferred from the distribution of distant radio galaxies and quasars, pronounced quasars. The difference is not huge, but it is statistically significant, and if it holds up, it could have profound implications. One of the foundational assumptions of the Lambda-CDM model is called the cosmological principle. It states that, on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means the same everywhere. Isotropic means the same in every direction. This principle is what allows cosmologists to use a single set of equations to describe the entire universe. If the dipole discrepancy is real, it could mean that the universe is not as isotropic as we assumed. It could mean that there is a preferred direction in the universe, or that the expansion rate varies from one region to another. Either possibility would strike at the very heart of modern cosmology. Take a moment. Breathe gently. Notice how the mystery deepens with each layer we uncover. The universe is not just stranger than we thought. It is stranger than we can easily accommodate within the framework we built to describe it. You are safe here, in the dark, in the quiet. Let these ideas wash over you like gentle waves. There is no exam tomorrow. There is no need to remember every detail. Just let the story carry you. So, to summarize where we stand. The Lambda-CDM model, the standard model of cosmology, has been the foundation of our understanding of the universe for over 20 years. It describes a cosmos made of about 5% ordinary matter, 27% dark matter, and 68% dark energy, with the dark energy taking the form of a cosmological constant, a uniform, unchanging energy filling all of space. This model has been extraordinarily successful. It matches the cosmic microwave background. It matches the large-scale structure of the universe. It matches the abundances of light elements. It matches the observed expansion history inferred from distant supernovae. But cracks have appeared. The Hubble tension shows that the expansion rate measured locally does not match the expansion rate predicted from the early universe. The S8 tension shows that the universe is less clumpy than it should be. The JWST galaxies show that massive galaxies formed earlier than the model allows. And the CMB dipole anomaly hints that the universe may not be as uniform as we assumed. Each of these cracks, on its own, might not be fatal. But, together, they suggest that something fundamental is missing from our picture. Some new physics, some overlooked ingredient, some deeper truth about the nature of space and time and energy that we have not yet grasped. And it is in this context that the most dramatic crack of all emerged. A crack not in the periphery of the model, but at its very core. In dark energy itself. Section 4. Dark energy is breaking. In the spring of 2024, a group of scientists gathered at a conference in Switzerland to present the first results from one of the most ambitious astronomical projects ever attempted. The project is called DESI, which stands for the Dark Energy Spectroscopic Instrument, and what they announced would send tremors through the entire field of cosmology. DESI is a machine designed to answer one question. Is dark energy constant, or is it changing? This is, in many ways, the most important question in all of cosmology right now. Because if dark energy is constant, then the Lambda-CDM model survives. The cracks we discussed, the Hubble tension, the S8 tension, the impossible galaxies, would need to be explained by other means, perhaps calibration errors, perhaps unknown astrophysical effects, perhaps a combination of small, mundane corrections. But if dark energy is changing, then the model breaks, and we need something new. The instrument is installed on the Mayall 4-meter telescope at the Kitt Peak National Observatory in Arizona. It consists of 5,000 tiny robotic positioners, each one capable of independently aligning an optical fiber with a target galaxy or quasar. In a single observation, DESI can simultaneously record the spectra of 5,000 objects. A spectrum is the breakdown of an object's light into its component wavelengths, like a prism splitting white light into a rainbow. From a spectrum, astronomers can determine an object's distance with high precision by measuring its redshift. Over its 5-year survey, DESI aims to map the three-dimensional positions of roughly 40 million galaxies and quasars, spanning a volume of the universe so large that it dwarfs all previous surveys combined. The goal is to measure the expansion history of the universe with unprecedented precision, charting how the expansion rate has changed over the past 11 billion years. And the key to this measurement is something called baryon acoustic oscillations, often abbreviated as BAO, pronounced as individual letters BAO. To understand baryon acoustic oscillations, we need to return to the very early universe, to a time before the cosmic microwave background was released, when the universe was still a hot, dense plasma of protons, electrons, and photons. In this plasma, gravity and radiation were locked in a constant battle. Dark matter, which does not interact with light, began to clump together under gravity, forming the first density concentrations that would eventually grow into the cosmic web. But ordinary matter, the baryons, meaning protons and neutrons, was still coupled to the photons, the particles of light. The pressure from the photons pushed outward against the gravitational pull of the dark matter, creating a pattern of compression and rarefaction, regions where matter was squeezed together and regions where it was stretched apart. These are sound waves, literal sound waves, traveling through the plasma of the early universe at about half the speed of light. They are called baryon acoustic oscillations because they involve baryons, ordinary matter, oscillating acoustically, like sound waves. The sound waves traveled outward from the initial density concentrations, like ripples spreading from a stone thrown into a pond. They traveled at a well-defined speed, determined by the temperature and composition of the plasma. And they traveled for a well-defined amount of time, roughly 380,000 years, until the universe cooled enough for atoms to form and the photons decoupled from the matter. At that moment, the sound waves froze. They stopped propagating. The ripples were frozen into the distribution of matter, leaving a characteristic imprint. A slight excess of matter at a specific distance from each initial density peak. That distance, the distance a sound wave could travel in 380,000 years, is about 150 megaparsecs in today's universe, or roughly 500 million light-years. This is the BAO scale. It is a cosmic ruler, imprinted in the distribution of matter at the dawn of time and still visible in the clustering of galaxies today. When scientists plot the statistical distribution of galaxy separations, they see a slight bump, a small but measurable excess of galaxy pairs separated by about 500 million light-years. This bump is the BAO signal. Because the BAO scale is known, because we can calculate it from first principles using well-understood physics, it serves as a standard ruler. By measuring the apparent size of the BAO signal at different epochs, at different redshifts, scientists can determine the distance to that epoch, and by tracking how the BAO scale changes with redshift, they can map the expansion history of the universe. This is what DESI does. By measuring the positions of millions of galaxies, it maps the BAO signal at many different redshifts, building a detailed expansion history that spans most of cosmic time. Now, here is where it gets interesting. If dark energy is a cosmological constant, truly constant, never changing, the same today as it was 10 billion years ago, then the expansion history should follow a very specific pattern. The BAO measurements should trace out a very specific curve. DESI was designed to test this with extraordinary precision. To describe how dark energy behaves, cosmologists use a parameter called W, pronounced simply as W. This parameter describes the relationship between dark energy's pressure and its density, a quantity known as the equation of state. For a cosmological constant, W is exactly -1. This means dark energy has a specific fixed relationship between its pressure and density that never changes. If W is different from -1, it means dark energy is not a cosmological constant. It is something else, something more dynamic, something that evolves over time. To capture the possibility that W might change over time, cosmologists often use a two-parameter description. The first parameter, called W0, represents the value of W today. The second parameter, called WA, represents how much W has changed over the history of the universe. If W minus A is 0, dark energy's equation of state has been constant. If W minus A is not 0, dark energy has been evolving. In the Lambda-CDM model, W minus 0 equals -1 and W minus A equals 0. Dark energy is constant. End of story. DESI tested this prediction, and the result was startling. When the DESI collaboration combined their BAO measurements with data from the cosmic microwave background and Type 1a supernovae, they found evidence that dark energy is not constant. The data favored values of W0 greater than -1 and WA less than 0. In simpler terms, the data suggested that dark energy was weaker in the past than it is today, and that its strength has been increasing over time. Let me unpack what this means, because it is genuinely extraordinary. If dark energy is a cosmological constant, its density is the same everywhere and at all times. As the universe expands, the density of matter decreases, because the same amount of matter is spread over a larger volume. But the density of a cosmological constant stays the same. 1 cubic meter of space has the same amount of dark energy today as it did 10 billion years ago, and as it will 10 billion years from now. But the DESI data suggests something different. It suggests that the density of dark energy has been changing. In the early universe, dark energy was weaker, contributing less to the expansion. Over time, it has grown stronger, contributing more. The cosmic acceleration we observe today may be a relatively recent phenomenon, not a permanent feature of the universe. This is not a small revision. If dark energy is evolving, it is not a cosmological constant. It is not vacuum energy. It is something else entirely, something dynamic, something that changes with time. and that means the entire Lambda-CDM framework, the foundation of modern cosmology, is incomplete. When the DESI results were first presented in April of 2024, the statistical significance was intriguing but not conclusive. The data disfavored a cosmological constant at roughly the 2 to 3 sigma level, depending on which combination of datasets was used. In physics, a 2 to 3 sigma result is suggestive but not definitive. It means there is roughly a 1 to 5% chance the result is a statistical fluctuation. But there was an important detail that made the result more compelling than the bare statistical significance might suggest. The DESI data was consistent with the direction suggested by other independent measurements. The Hubble tension, for example, might be alleviated if dark energy was weaker in the past, because changing the dark energy history changes the predicted expansion rate today. The S8 tension might also be reduced, because changing dark energy affects how structure grows over time. In other words, the DESI result was not an isolated anomaly. It was pointing in the same direction as the other cracks in the Lambda-CDM model. And when multiple independent measurements all point the same way, even if no single measurement is definitive on its own, the cumulative evidence becomes harder to ignore. Then, in 2025, DSE released its second set of results, based on additional data from the ongoing survey. And the evidence for evolving dark energy grew stronger. The second data release included more galaxies, more quasars, more precise BAO measurements at more redshifts. And the trend continued. The data continued to favor WA less than 0, meaning dark energy that was weaker in the past and stronger today. The statistical significance increased. Different analysis methods, different data combinations, different systematic error treatments all pointed in the same direction. The cosmological constant was looking increasingly uncomfortable. Now, I want to be very careful here. Science does not progress by press release. A 2 or 3 sigma result, or even a 4 sigma result, is not a discovery. In particle physics, the standard for a discovery is 5 sigma, roughly a 1 in 3.5 million chance of a false positive. Cosmology has traditionally used a lower threshold, but even so, the DESI results are not yet at the level where scientists would confidently declare that Lambda-CDM is dead. There are systematic uncertainties that still need to be fully understood. The BAO measurements depend on the galaxy survey being properly calibrated. The combination with supernova data depends on the supernova measurements being consistent across different surveys, and there have been hints of tension between different supernova datasets. The combination with CMB data assumes that the CMB analysis itself is correct, and there are ongoing debates about certain aspects of the Planck analysis. Moreover, the specific parameterization used, the W0 and WA framework, is a simplified description. Real dark energy, if it is truly dynamic, might behave in ways that are not well captured by just 2 parameters. The results depend, to some degree, on the mathematical model used to describe the data. All of these caveats are important. They are the reason why no reputable scientist has declared the cosmological constant dead. What they have said, almost unanimously, is that the DESI results are the most intriguing and potentially revolutionary finding in cosmology in years. They are a hint, a strong hint, a hint that something new may be lurking in the data. But let us take a step back and think about what it would mean if dark energy really is evolving. What would that tell us about the nature of reality? If dark energy is a cosmological constant, it is a property of space itself. It is the intrinsic energy of the vacuum. It is always there, everywhere, unchanging. This is simple but deeply mysterious because of the cosmological constant problem we discussed earlier. The predicted value of vacuum energy is 120 orders of magnitude larger than the observed value, and no one knows why. If dark energy is not a cosmological constant, if it is changing over time, then it is probably not vacuum energy. It is probably a new field, a new fundamental entity pervading all of space, with its own dynamics and its own evolution. The most popular theoretical candidate for dynamic dark energy is called quintessence, pronounced quintessence. Quintessence is a hypothetical scalar field, similar in some ways to the Higgs field that gives particles their mass, but operating on cosmological scales. Unlike a cosmological constant, which has a fixed energy density, a quintessence field can evolve over time. Its energy density can increase or decrease, depending on the details of its potential energy landscape. Think of it this way. Imagine a ball rolling slowly down a hill. The ball's potential energy depends on where it is on the hill. As it rolls, its energy changes. A cosmological constant would be like a ball sitting perfectly still on a perfectly flat plane, with the same energy everywhere and always. Quintessence would be like a ball rolling down a gentle slope, with its energy changing as it moves. The DESI data, if it holds up, is more consistent with a quintessence-like scenario than with a cosmological constant. The data suggests that dark energy's equation of state has changed over time, starting from a value less negative than -1 in the past and becoming more negative, approaching -1 or even going beyond it in the present. This is exactly the kind of behavior you would expect from a slowly evolving field. But there is an even more exotic possibility. What if the equation of state parameter W crosses below -1? What if W goes below -1? A cosmological constant has WW exactly equal to -1. If W is between 0 and -1, you have a quintessence-like field with relatively conventional physics. But if W goes below -1, you enter a regime called phantom dark energy. And phantom dark energy is genuinely terrifying. In normal physics, as the universe expands, things get diluted. The density of matter decreases because the same mass is spread over a larger volume. Even a cosmological constant maintains a constant density, never decreasing but never increasing either. Phantom dark energy is different. As the universe expands, the density of phantom dark energy increases. The more the universe expands, the stronger phantom dark energy becomes. And the stronger it becomes, the faster the universe expands. And the faster the universe expands, the stronger it becomes. It is a runaway feedback loop, an escalating cycle that, if left unchecked, leads to one of the most dramatic possible endings for the universe. The Big Rip. In a Big Rip scenario, the accelerating expansion of the universe eventually becomes so violent that it tears apart everything. First, the largest structures in the universe, galaxy clusters and the cosmic web, are pulled apart. Then, individual galaxies are disrupted. Then, star systems are torn apart, with planets ripped away from their stars. Then, planets themselves are destroyed, their material dispersed. Then, atoms are pulled apart. Then, atomic nuclei. Then, in the final moments, space itself is ripped apart at the subatomic level. The Big Rip is, mercifully, far from certain. The current data does not strongly favor phantom dark energy. The DESI results are more consistent with quintessence-like behavior, where W is close to -1 but does not cross below it. But the uncertainties are still large enough that phantom dark energy has not been ruled out. The fact that we are even discussing these possibilities tells you how much the landscape of cosmology has shifted in just a few years. A decade ago, the Lambda-CDM model seemed unassailable. The cosmological constant was the simplest, most elegant explanation for dark energy, and all the data supported it. Today, the most precise measurements we have are hinting that the cosmological constant may not be the right answer, that dark energy may be dynamic, that the universe may be evolving in ways we did not anticipate, and the implications do not stop at dark energy. If dark energy is not a cosmological constant, it changes everything else too. It changes the predicted age of the universe. It changes the predicted growth of structure. It changes the predicted distances to galaxies. It changes the predicted power spectrum of the CMB. In short, if dark energy is evolving, the entire standard model of cosmology needs to be revised, not discarded necessarily. Many of its core elements would survive. The Big Bang, the cosmic microwave background, the formation of structure through gravitational collapse, all of these would remain. But the precise numerical framework, the specific parameters, the detailed predictions, all of that would need to be recalculated with a new model of dark energy. This is not a disaster. It is an opportunity, one of the most exciting opportunities in the history of physics. Because if dark energy is dynamic, it means there is new physics out there to be discovered. New fields, new forces, new fundamental principles that we have not yet identified. The universe is trying to tell us something through the language of data, and we are just beginning to learn how to listen. Rest now if you need to. Let the idea of a universe in flux carry you gently. Nothing is static. Nothing is permanent. Even the force that shapes the destiny of the cosmos may be changing, evolving, becoming something new. There is something comforting in that, if you think about it. The universe is not finished. It is still becoming. And if dark energy is truly evolving, then the cosmos is not a machine running on fixed rules. It is more like a living thing, adapting, changing, growing into something it has not been before. What kind of universe are we living in? A year ago, most cosmologists would have answered that question with confidence. A Lambda-CDM universe. A universe with a cosmological constant. A universe whose fate, the Big Freeze, was essentially sealed. Today, that confidence has been shaken. The data from DESI, combined with the other tensions and anomalies we have discussed, paints a picture of a universe that is more complex, more dynamic, and more mysterious than the standard model suggests. And the next few years of data from DESI and from the other experiments that are now coming online will determine whether this picture holds up or whether it fades back into the statistical noise. Either way, we are living through a pivotal moment in the history of cosmology. A moment when the standard model is being tested as never before. A moment when the answers to the biggest questions in science are genuinely up for grabs. Section 5. The Fate of Everything. Now we come to the most profound question that cosmology can ask. What is the ultimate fate of the universe? How does it all end? For most of the 20th century, this question had a relatively straightforward answer, at least in principle. The fate of the universe depends on how much matter it contains. If there is enough matter, Gravity will eventually halt the expansion and pull everything back together in a great cosmic collapse, a scenario known as the Big Crunch. If there is not enough matter, the expansion will continue forever, and the universe will gradually grow colder and darker as stars burn out and galaxies drift apart, a scenario known as the Big Freeze, or sometimes the heat death. The discovery of the accelerating expansion in 1998 complicated this picture dramatically. If dark energy continues to drive the expansion faster and faster, then the Big Crunch is off the table. The universe will not collapse. Instead, it will expand forever, at an ever-increasing rate. But the details of that expansion, and the ultimate fate of everything in the universe, depend entirely on the nature of dark energy. Is it constant? Is it evolving? Is it getting stronger or weaker? The answer to these questions determines which ending the universe gets. And, as we have just seen, we are no longer confident that we know the answer. Let us explore the possibilities. Scenario 1. The Big Freeze. This is the fate predicted by the Lambda-CDM model, with dark energy as a cosmological constant. In this scenario, dark energy has a constant density that never changes. The universe continues to expand at an accelerating rate, but the acceleration itself remains steady. Over time, the consequences of this expansion become increasingly dramatic. Galaxies that are not gravitationally bound to our own local group will gradually recede from us, moving faster and faster until they cross the cosmological horizon, the boundary beyond which light can never reach us due to the expansion of space. One by one, distant galaxies will fade from view, their light redshifted into oblivion. Within our own galaxy, and within the local group of galaxies that includes the Milky Way, Andromeda, and several dozen smaller galaxies, life will continue for a very long time. These galaxies are bound together by gravity, and they will eventually merge. The Milky Way and Andromeda are on a collision course, expected to merge in roughly 4 to 5 billion years, forming a single, larger galaxy sometimes called Milkomeda or Milkdromeda. But beyond the local group, the universe will grow increasingly empty and dark. Stars will continue to form for perhaps another 100 trillion years, as long as there is gas available to fuel them. But eventually, the gas will be used up. The last stars will burn out. The universe will be left with only stellar remnants, white dwarfs, neutron stars, and black holes slowly cooling in an ever-expanding void. The white dwarfs will radiate away their remaining heat over quadrillions of years, fading from white to yellow to red to infrared to invisible. Neutron stars will do the same. Even the black holes, the most long-lived objects in the universe, will eventually evaporate through a process called Hawking radiation, named after the physicist Stephen Hawking, who predicted it in 1974. Hawking radiation arises from quantum effects near the event horizon of a black hole. Virtual particle pairs, which normally appear and annihilate each other in empty space, can be split by the extreme gravitational field near the horizon. One particle falls into the black hole while the other escapes. The escaping particle carries away a tiny amount of the black hole's energy, and, over time, this causes the black hole to lose mass and shrink. For a stellar mass black hole, this process is unimaginably slow. It would take roughly 10 to the power of 60, 7 years for a solar mass black hole to evaporate completely. For a supermassive black hole, the kind found at the centers of galaxies, the timescale is even longer. roughly 10 to the power of 100 years or more. But eventually, even the supermassive black holes will evaporate. And when the last black hole evaporates, the universe will be left with nothing but a thin, cooling gas of photons, neutrinos, and perhaps a few elementary particles, spread across an incomprehensibly vast and still expanding void. This is the heat death, the state of maximum entropy, the state in which no further work can be done, no further structure can form, no further information can be processed. It is not a dramatic ending. It is a slow, gentle fading into absolute darkness and silence. Of all the possible fates of the universe, the Big Freeze is, in a sense, the most peaceful. The universe does not end with a bang. It ends with a whisper that goes on forever. There is a haunting beauty to this vision. A universe that began in unimaginable violence, in the searing heat of the Big Bang, ending in perfect silence, the temperature dropping asymptotically toward absolute zero, the last particles drifting through an empty void, separated by distances so vast that no signal could ever bridge them. A cosmos that is not dead exactly, because death implies a previous state of life, but a cosmos that has exhausted every possibility. Every reaction that could happen has happened. Every star that could form has formed and burned out. Every structure that could exist has existed and dissolved. There is nothing left but the slow, eternal cooling of space itself. Physicists sometimes call this the era of darkness, and it would last, in a sense, forever. Not just billions of years, not just trillions, but an eternity of emptiness, stretching forward without limit long after every trace of structure and complexity has been erased. Scenario 2. The Big Rip. We touched on this briefly in the previous section, but let us explore it more fully. The Big Rip occurs if dark energy is of the phantom type, with an equation of state parameter WW less than -1. In this case, the density of dark energy increases as the universe expands, leading to a runaway acceleration that eventually overcomes every other force in the universe. The timeline of the Big Rip depends on the exact value of W. The more negative W is, the sooner the Big Rip occurs. For a value of W equal to -1.5, the Big Rip would occur roughly 22 billion years from now. For a value closer to -1, the Big Rip would be pushed further into the future. The progression would unfold in stages. Roughly 1 billion years before the Big Rip, galaxy clusters would be torn apart. The gravitational bonds holding clusters together would be overwhelmed by the expansion of space. Galaxies that had been orbiting within clusters for billions of years would be flung apart. About 60 million years before the Big Rip, individual galaxies would be disrupted. The gravitational force holding stars in their orbits around the galactic center would be overwhelmed. Stars would scatter, streaming outward into the expanding void. About 3 months before the Big Rip, solar systems would be torn apart. The gravitational bond between a star and its planets would be broken. Planets would be cast adrift, floating freely in an ever-expanding universe. About 30 minutes before the Big Rip, planets would be destroyed. The gravitational force holding a planet together would be overwhelmed by the expansion. The Earth, if it still existed, would be pulled apart into fragments. About 10 to the power of -19 seconds before the Big Rip, atoms would be torn apart. The electromagnetic force holding electrons to atomic nuclei would be overwhelmed. All matter would be reduced to a plasma of free particles. And finally, at the moment of the Big Rip itself, The fabric of space itself would be torn apart at the subatomic level. The expansion rate would become infinite. The universe would end not in cold darkness, but in a violent, all-encompassing destruction of the very structure of reality. The Big Rip is the most dramatic possible fate of the universe. It is also, at the moment, not the most likely. The current data from DESI and other experiments suggests that W is close to -1, probably slightly above it, rather than below. But the uncertainties are still large enough that the Big Rip cannot be ruled out. And as we continue to collect data, the picture may change. There is something strangely poetic about the Big Rip, if you are willing to see it that way. The universe began with everything compressed into a single point. And in the Big Rip, the universe ends with everything pulled infinitely far apart. It begins as the ultimate togetherness and ends as the ultimate loneliness. Every particle in the universe, separated from every other particle by infinite distance. But let us not dwell too long on that thought. The night is meant for rest, not existential dread. The Big Rip is just one possibility, and not the most likely one. There are gentler endings. Scenario 3. The Big Crunch. This is the opposite of the Big Rip. Instead of dark energy growing stronger and tearing the universe apart, dark energy grows weaker and eventually reverses its effect, allowing gravity to reassert itself and pull the universe back together. If dark energy is dynamic and its density is decreasing over time, there is a possibility, however speculative, that dark energy could eventually become negative. If dark energy's contribution to the expansion turns from repulsive to attractive, it would add to gravity rather than opposing it. The expansion would slow, halt, and reverse. The universe would begin to contract. As the contraction accelerated, galaxies would move closer together. The temperature of the cosmic microwave background would increase, rising from its current frigid 2.7 Kelvin as the background radiation was blue shifted by the contracting space. The sky, instead of being dark and cold, would gradually grow brighter and hotter. Eventually, the contraction would become so violent that galaxies would merge, stars would collide, and all the matter in the universe would be compressed back into a hot, dense state reminiscent of the Big Bang. This is the Big Crunch, the mirror image of the beginning, a cosmic collapse that ends with all of existence compressed into a singularity. Some physicists have speculated about what might happen after the Big Crunch. Could the singularity bounce, triggering a new Big Bang and a new cycle of expansion and contraction? This idea is called the cyclic model or the oscillating universe, and it has a long history in both physics and philosophy. The idea of an eternally oscillating universe, expanding and contracting forever, is aesthetically appealing. But whether it is physically possible remains deeply uncertain. The Big Crunch scenario requires dark energy to not only evolve, but to reverse its sign, becoming gravitationally attractive. This is a much more dramatic departure from the cosmological constant than what the current data suggests. At the moment, the DESI results favor dark energy that is evolving, but still repulsive, still driving acceleration, just not at a constant rate. The Big Crunch remains the least likely of the three scenarios, but it is not impossible. Scenario 4. Something entirely unexpected. Perhaps the most honest assessment of the ultimate fate of the universe is that we simply do not know. Our predictions depend on our understanding of dark energy, and our understanding of dark energy is, as we have seen, incomplete, and possibly fundamentally wrong. There are theoretical frameworks that predict fates for the universe that do not fit neatly into any of the three categories above. For example, some models of dark energy predict a scenario called the Big Freeze-Out, where dark energy undergoes a phase transition, similar to water freezing into ice, and the nature of space itself changes abruptly. Other models predict that the universe could tunnel through a quantum mechanical process from its current state to a different, lower energy state, a scenario sometimes called vacuum decay. Vacuum decay is a particularly unsettling possibility. In this scenario, the Higgs field, which is responsible for giving particles their mass, may not be in its lowest energy state. It may be in what physicists call a metastable state, a local minimum of energy that is not the true, deepest minimum. If the Higgs field were to quantum tunnel from its current state to the true minimum, the result would be a bubble of true vacuum, expanding at the speed of light, converting everything it touches into a completely different form of matter, with different physical laws. Inside the bubble, the masses of particles would change. The strengths of the fundamental forces would change. Atoms, as we know them, might not be possible. Life, as we know it, would be impossible. And because the bubble expands at the speed of light, there would be no warning. One moment, everything is normal. The next moment, a wall of altered physics arrives, and everything changes instantaneously. The probability of vacuum decay is thought to be extremely low, and the timescale is thought to be extraordinarily long, far longer than the current age of the universe. But it is a reminder that the fate of the cosmos may depend on physics we do not yet understand, in ways we cannot yet predict. The DESI results have reopened the question of cosmic destiny in a way that has not been possible for 2 decades. If dark energy is constant, the future is the big freeze, and it is settled. But if dark energy is evolving, the future is uncertain. The universe may expand, forever, but at a different rate than we expected. It may eventually recollapse. It may undergo a phase transition. It may do something we have not even imagined. This is simultaneously humbling and thrilling. Humbling because it reminds us how little we truly understand about the fundamental nature of the cosmos, and thrilling because it means there are still great discoveries to be made. The fate of the universe is not written. It is being written right now in the data from telescopes and satellites, in the equations of theorists, in the slow accumulation of evidence that will, one day, tell us how the story ends. For tonight, though, let the question remain open. There is no need to resolve it before you sleep. The universe will still be here in the morning, expanding, evolving, becoming, and you will be part of it, as you have always been, made of the same atoms that were forged in the first minutes after the Big Bang, the same stardust that has been cycling through the cosmos for 13.8 billion years. Section 6. The New Cosmology. We have arrived at the final chapter of tonight's journey, and it is, perhaps surprisingly, a chapter not of despair, but of hope. Because the crisis in cosmology, for all its unsettling implications, is exactly the kind of crisis that drives science forward. The greatest breakthroughs in physics have always come from moments when the existing framework failed, when the observations refused to match the predictions, when the data said something the theories could not explain. Newton's laws of motion worked perfectly for over 200 years, predicting the motions of planets and cannonballs and tides with extraordinary precision. But they could not explain the peculiar orbit of Mercury, the innermost planet, which was slowly rotating in a way that Newton's gravity could not account for. It took Einstein's general theory of relativity, published in 1915, to explain that tiny discrepancy. And general relativity did not just fix the Mercury problem. It revealed an entirely new understanding of gravity, space, and time. The same pattern has repeated throughout the history of physics. The failure of classical physics to explain black body radiation led to quantum mechanics. The failure of Newtonian gravity to account for the bending of starlight led to general relativity. The failure of classical electromagnetism to explain the photoelectric effect led to the concept of photons and the quantum nature of light. Every crisis in physics has been a doorway to deeper understanding, and the crisis in cosmology today has all the hallmarks of the next great doorway. So, what comes next? What are the experiments and observations that will, over the coming years, determine whether dark energy is truly evolving, whether Lambda-CDM needs to be replaced, and what the new model of the universe might look like? The first and most obvious is the continuation of the DESI survey itself. DESI is still collecting data. Its original, 5-year survey will produce an even larger galaxy catalog, with more precise BAO measurements at more redshifts. Each additional year of data will tighten the constraints on the dark energy equation of state, either confirming the hint of evolution or pushing the data back toward the cosmological constant. But DESI is not alone. A new generation of cosmological surveys is coming online, each one designed to test the Lambda-CDM model in different ways. The Vera C. Rubin Observatory, currently under construction in Chile, is named after the astronomer Vera Rubin, who provided some of the first compelling evidence for dark matter through her observations of galaxy rotation curves. The Rubin Observatory's Legacy Survey of Space and Time, often called LSST, will image the entire visible sky repeatedly over 10 years, cataloging billions of galaxies and tracking changes over time. LSST will measure the growth of cosmic structure through gravitational lensing, providing independent constraints on dark energy and the S8 tension. The Euclid Space Telescope, launched by the European Space Agency in 2023, is designed specifically to study dark energy and dark matter. Euclid will map the shapes and positions of billions of galaxies over about 1/3 of the sky, measuring both gravitational lensing and galaxy clustering with unprecedented precision. Its data will complement DESI's BAO measurements, providing an independent test of whether dark energy is constant or evolving. The Nancy Grace Roman Space Telescope, planned for launch by NASA, will carry a wide-field infrared camera capable of surveying large areas of the sky at near-infrared wavelengths. Roman will measure the expansion history through both supernovae and BAO, providing yet another independent dataset. Together, these observatories will produce a flood of cosmological data unlike anything we have seen before. By the end of this decade, we will have measurements of the expansion history, the growth of structure, and the distribution of matter that are orders of magnitude more precise than what we have today. If dark energy is evolving, these experiments will confirm it. If it is constant, they will prove it. Either way, we will know. On the theoretical side, the crisis has sparked a renaissance of new ideas. Physicists are exploring a wide range of models that go beyond the simple cosmological constant. Quintessence models, as we discussed, posit a new scalar field that evolves over time. There are many different versions of quintessence, differing in the shape of the field's potential energy function, and each one makes different predictions for how dark energy evolves. The DESI and other survey data will be able to distinguish between many of these models. Some theorists are exploring modifications to general relativity itself. Perhaps the accelerating expansion is not caused by a new form of energy at all, but by a breakdown of Einstein's theory on cosmological scales. Modified gravity theories such as F of R gravity, Gauss-Bonnet gravity, and others can mimic the effect of dark energy without invoking a new energy component. These theories make different predictions from quintessence and from the cosmological constant, and the upcoming observational data will help distinguish between them. Others are exploring the possibility that the Hubble tension is caused by new physics in the early universe, before the CMB was emitted. Models of early dark energy posit a brief period of additional dark energy in the first few 100,000 years after the Big Bang, which then disappeared, altering the expansion rate in a way that could reconcile the CMB and distance ladder measurements. These models are controversial, and they have their own tensions with the data, but they represent a creative attempt to resolve the crisis. There are also more radical proposals. Some physicists have suggested that the cosmological constant problem, the enormous discrepancy between the predicted and observed vacuum energy, might be resolved by the existence of a vast landscape of possible universes, each with different values of the cosmological constant. In this multiverse picture, our universe has a small cosmological constant simply because that is the value that allows galaxies, stars, and life to form. Universes with larger values of the cosmological constant would expand too rapidly for structure to form, and would be sterile and empty. This anthropic reasoning, as it is called, is controversial. Many physicists find it unsatisfying, because it does not explain why the cosmological constant has the value it does. It merely says that if it had a different value, we would not be here to observe it. It is an explanation that explains everything and nothing simultaneously. But whether or not the multiverse is real, the sheer diversity of theoretical ideas being explored is a sign of a healthy, vibrant field, grappling with a genuine mystery. This is what physics looks like when it is on the verge of a breakthrough. Not certainty, but ferment. Not answers, but better questions. There is also the tantalizing possibility that the resolution of the dark energy crisis will come from an unexpected direction entirely. Some of the most important discoveries in science have been serendipitous, found while looking for something else. Penzias and Wilson found the cosmic microwave background while trying to eliminate noise from a radio antenna. Hubble discovered the expanding universe while trying to classify galaxies. The discovery of the accelerating expansion itself was a surprise. Both supernova teams expected to find the expansion slowing down. Perhaps the key to dark energy lies not in the large-scale surveys of galaxies, but in a laboratory experiment, a particle physics discovery, a new mathematical insight, or an observation in a completely different field. Perhaps the answer is already hidden in data we have already collected, waiting to be noticed by someone who looks at it from the right angle. This is the beauty of science. You never know where the answer will come from. You only know that if you keep looking, keep measuring, keep questioning, the universe will eventually reveal its secrets. And there is one more thing worth saying about the new cosmology. It will change not just our understanding of the universe, but our understanding of ourselves. For most of human history, we believed we were at the center of everything. The Earth was the center of the universe. The sun revolved around us. The stars were fixed lights on a celestial sphere surrounding our world. Copernicus showed us that the Earth revolves around the Sun. Galileo confirmed it. Herschel showed us that the Sun is just one star among billions in a vast galaxy. Hubble showed us that our galaxy is just one among billions in an expanding universe. And now, the crisis in cosmology is showing us something even more humbling. Not only are we not at the center of the universe, we are not even made of the same stuff as most of the universe. The atoms that make up our bodies, the protons and neutrons and electrons, the fundamental building blocks of everything we have ever experienced, account for only 5% of the cosmos. The rest is dark matter and dark energy, substances we have never touched, never seen, never understood. We are a tiny minority, floating on a thin film of ordinary matter, in a universe dominated by forces and substances that are completely alien to our experience. And yet, from this tiny sliver of ordinary matter, consciousness emerged. From atoms and molecules, life arose. From life, intelligence. From intelligence, science. And from science, the extraordinary ability to look out at the cosmos and begin to understand it. We may be small. We may be made of the minority ingredient. But we are the part of the universe that figured out the rest. And that is not nothing. That is, in fact, everything. Let us step back now and take in the full sweep of what we have explored tonight. We began with the night in 1998, when two teams of astronomers discovered that the expansion of the universe is accelerating, driven by a mysterious force called dark energy. We traced the history of how scientists built the Lambda-CDM model, the standard model of cosmology, which describes a universe made of 5% ordinary matter, 27% dark matter, and 68% dark energy. We examined the cracks that have appeared in this model. The Hubble tension, where two precise measurements of the expansion rate refuse to agree. The S8 tension, where the universe is less clumpy than the model predicts. The impossible galaxies, where JWST found massive galaxies in the early universe that the model says should not exist. And the CMB dipole anomaly, which hints that the universe may not be as uniform as we assumed. We explored the most dramatic crack of all, the DESI results suggesting that dark energy is not constant, that it is evolving over time, growing stronger as the universe expands. If confirmed, this would mean that dark energy is not a cosmological constant, not vacuum energy, but something new, something dynamic, something we have never encountered before. We considered the implications for the fate of the universe. The Big Freeze, where the universe expands forever into cold darkness. The Big Rip, where phantom dark energy tears apart everything, down to the atoms themselves. The Big Crunch, where the universe reverses its expansion and collapses back into a singularity. And the possibility that the true fate is something we have not yet imagined. And we looked to the future, to the experiments and ideas that will, over the coming years, determine which of these scenarios is correct. DSI, the Rubin Observatory, Euclid, the Roman Space Telescope, quintessence, modified gravity, early dark energy, the multiverse. The crisis in cosmology is real. The model that served us so well for 20 years is showing its age. The cracks are multiplying. The data is telling us that something is missing, something fundamental, something that we have not yet understood. But this is not a cause for despair. It is a cause for wonder. Because behind every crisis in physics lies a deeper truth, waiting to be uncovered. Newton's gravity gave way to Einstein's general relativity, which was not a rejection of Newton, but an expansion, a deeper, more complete understanding that contained Newton's laws as a special case. Whatever replaces Lambda-CDM will not reject the Big Bang, or the cosmic microwave background, or the expansion of the universe. It will build on them. It will encompass them. And it will reveal new truths that we cannot yet imagine. We stand at the edge of a new cosmology, a cosmology where dark energy is not a fixed property of space, but a living, evolving field that changes with time, a cosmology where the fate of the universe is not sealed, but open, contingent, still being written, a cosmology where the biggest questions, the questions about the origin, the nature, and the destiny of everything, are still gloriously unanswered. And perhaps that is the most appropriate thought to carry with you into sleep tonight. The universe is not finished revealing itself to us. There are secrets still hidden in the light of distant galaxies, in the patterns of cosmic structure, in the whisper of the cosmic microwave background. Secrets that the next generation of telescopes will uncover. Secrets that will reshape our understanding of reality in ways we cannot predict. You are part of this universe. Your atoms were forged in the hearts of stars that burned billions of years before the Earth was born. The calcium in your bones was created in the explosive death of a massive star. The iron in your blood was synthesized in a supernova. The hydrogen in the water that makes up most of your body has existed since the first few minutes after the Big Bang. You are the universe examining itself. You are 13.8 billion years of cosmic evolution, compressed into a conscious being, lying in the dark, wondering about the fate of everything. And the fact that you can wonder, the fact that atoms arranged in the pattern of your brain can contemplate the expansion of space and the nature of dark energy, is perhaps the most remarkable thing of all. The universe gave rise to consciousness. And now consciousness is trying to understand the universe. This is the Great Circle, the cosmic feedback loop, the deepest mystery woven into the fabric of reality. The stars are still burning tonight. The galaxies are still turning. The cosmic web is still growing, thread by thread, node by node, across the vast expanding void. And dark energy, whatever it is still doing its work, gently, invisibly, pushing the universe apart in ways we are only beginning to understand. Let that gentle push carry you now. Let the expansion of the cosmos be the expansion of your breath, slow and steady and unstoppable. There is nowhere you need to be, nothing you need to do. The universe has been doing its thing for 13.8 billion years without your help, and it will continue for billions more. You are safe. You are warm. You are a temporary arrangement of ancient stardust, resting in the dark, on a small blue world orbiting an ordinary star, in the quiet suburbs of a spiral galaxy that is drifting through a universe whose fate is still unknown. And that is enough. That is more than enough. That is everything. Good night. And thank you for joining me tonight, here on the Science Pillow. The cosmos will be here when you return.